All right, today we're going to go through the last section of Chapter 7, and we're going to introduce our last two types of quadrilaterals called trapezoids and kites. We're going to kind of talk about what they are and then talk about their special properties and kind of how you're going to see them being used on the homework and on future quizzes and tests. So we start with the trapezoid. And so as far as the definition, when we're looking at a trapezoid, it is a quadrilateral. So it's a four-sided object with exactly one pair of parallel sides. So this differs quite a bit from our parallelograms in that in parallelograms, both sets of sides were parallel. In this case, for our trapezoid, we're only going to have one single pair of parallel sides. So in the picture that we see below here, this top side AB would be parallel to this top or bottom side CD, but the two sides, the left and right side, are not parallel. They don't go the same direction. And so in any trapezoid, we're always going to have just one single set. And so we could have it oriented like this, or they could even do something like this, where they have it kind of on its side. And so as we're looking at this, then we can see this left side is parallel to this right side, and then the top and bottom go different directions. So anytime you see a figure where one set of sides is parallel and the others are not, you know that that's a trapezoid. And so any trapezoid, some of the things that we need to know, some terminology, when we talk about the bases. So each trapezoid has two bases, and in this case, those are the parallel sides. So our bases are the parallel sides of my trapezoid, which in this case would be side AB and side CD. So whatever two sides are the parallel sides, those are going to be your bases. So even if it was sideways, the left side and right side, if they're parallel, they're going to be the bases. The legs then, so the legs are the non-parallel sides. So those are the two sides that are not going the same direction. And so in this case, that would be like side AD and side BC. And so knowing which two sets of sides we're working with, whether it's the bases or the legs, is going to be important based on what we're trying to do with the problem. The last term that we definitely need to make sure we know are what we call the base angles. So these are the angles along either of the two bases. So for base angles, they always come in pairs. So like this top side is one of my bases, AB. That means angle A and angle B are my base angles. So angle A and angle B would be a pair of base angles. Or we also have a second base on this trapezoid, which is down here at DC, which means angle D and angle C would also be a set of base angles. So as long as you're looking at the trapezoid, when you can identify those two bases, the two angles along each base are considered a pair of base angles. And then the other thing that we see on this slide here is that isosceles trapezoids. So a trapezoid in general just has two bases, two legs, and there's really nothing special about it other than the one set of parallel sides. In an isosceles trapezoid, one of the really key things here is that the two legs of the trapezoid are going to be congruent to each other. So in this case, if they told me this was isosceles, side AD and side BC would be congruent to each other. So that's a trapezoid with congruent legs. Now, isosceles trapezoids have some special properties that we want to make sure we talk about. Not only do they have the set of congruent legs like we see here, but if we're given an isosceles trapezoid, then we are automatically knowing that base angles, so here angle D and angle C are along the same base, those two angles are going to be congruent. And then on the top side where the other base is, we have angle A and angle B are both base angles, so those two sets of angles are going to be congruent as well. So that's one of our big properties there. Base angles will always be congruent. The other thing is that the diagonals will be congruent. And so if I have my trapezoid and it's an isosceles and I draw in those diagonals here, then I know that AC, that diagonal, is going to be congruent to the other diagonal, BD, and so I can use that as well to find missing pieces. Now, the other thing I want to kind of discuss here, and it was something I kind of forgot to mention on that first slide, but when we're looking at trapezoids, the idea that the bases are parallel tell us something else about this trapezoid, and that is that if I jump from one base to another, so if I jump from the top base to the bottom base, my angles are going to add to 180. And so if I'm looking at this picture of this isosceles trapezoid, if for instance they told me that angle D was 70 degrees, then with that one single angle, I automatically know on the other side that angle C has to be 70 degrees. But not only that, when I jump to my other base angle, so when I jump up to the top here, they have to add to 180 with the bottom. So if the bottom is 70, the top would have to be 110, and then the other side would also have to be 110. Now that's something that happens in all trapezoids. So even if the base angles aren't congruent, when I jump from one base to the other, I'm always going to add to 180. So if I gave you another trapezoid here, I'm going to give you a little bit different orientation. So now it's on its side. This left side is parallel to the right side. Those are my bases. So if I look at this top left angle, let's say I told you it was 120, that means this angle here would have to be 60. Those are going to add to 180. But then on the bottom, this angle down here might only be 100 degrees. And so that means this angle across from it would have to be 80. So if it's just a regular trapezoid, the base angles aren't going to be the same, but when I go from one base to the other, I'm always going to have 180 degrees. So that's another thing to keep in mind as we're working through some of these problems today. Now the next thing we want to talk about with trapezoids is this idea of a mid-segment. Now we've talked about a mid-segment before when it pertained to triangles, and we're going to talk pretty much about the exact same thing here. So just like in triangles we had a mid-segment, trapezoids also do, and it's the one that joins the midpoints of the two legs. So we see that when we draw in line XY here, it cuts side BC in half, and it cuts side AD in half. So that's the mid-segment of my trapezoid. Now what's special about this mid-segment, first, is that it's going to be parallel to both of the bases. So it's going to be a parallel line to both bases, which means we can match up corresponding angles, like angle D and angle X up here, or angle C and angle Y. So that's going to be something that we might have to use at some point. So it's parallel to both of the bases. The other thing that's really important about this, and the one that we're going to probably use more often, is that the mid-segment is actually the average of the two bases. And what I mean by that is if I were to have both base values, so let's say I told you the top base was 10 units long and the bottom base was 30 units long, the mid-segment would have a length that's equal to the average of those two values. So what I have this formula over here, the mid-segment is base 1 plus base 2 over 2. What I'm talking about there is if I wanted to know the length of xy, I would take base 1, 30, plus base 2, 10, and then divide that by 2. And so 30 plus 10 is 40, divided by 2 is 20. There's my value for my mid-segment. Now, one thing that I would maybe mention here, and maybe a better way to think about this formula, because a lot of times kids freak out a little bit about fractions. So the other way I like to think about this formula is if I take 2 times the mid-segment, and I'm just going to abbreviate here. So if I take 2 times the mid-segment, that's equal to the base 1 plus the base 2. And a lot of times this is a much easier formula to work with because there's no fraction to have to worry about. And so this will be something that we kind of talk about in some of the future slides here. So when we look at the mid-segment, okay, if we're looking at something like this first example right here, we have both bases. We're looking for the value of the mid-segment. So that n value is going to be base 1 plus base 2, divided by 2. So 21 plus 33, which is going to be 54, divided by 2 is going to be 27. So I know it's got to be right in the middle of 21 and 33 like we talked about before. Now notice on the next one, we have one base, we have the mid-segment, we are looking for the other base. Now here's where that alternate version of the formula is really going to come into play here, because if I set it up normally, I'm going to have this fraction with n that's going to be a little bit tricky to solve. And so if I think about it the other way, if I take 2 of the mid-segment, so if I take 2 times the mid-segment, that's equal to 1 base plus the other base. And so now this is a much easier formula to solve, because now I take 2 times 18, which is 36. That's equal to n plus 14, and if I take 36 minus 14, n would equal 22. Now, in these types of problems, the other thing we have to be aware of is that they might not always just give us straight numbers like this. And in some cases, they might say something like AB is x plus 2, DC is 2x plus 5, and xy is 3x minus 10, or something like this. And so if we're looking at a problem like this, again, that second version of the formula, the one that we just did right over here, is probably going to be the way to go. Otherwise, we're going to have this fraction that makes things a little bit more complicated. So I would take 2 of the mid-segment. So 2 times my 3x minus 10 is equal to my 2 bases added together. So I would go ahead and distribute the 2. I would combine like terms here, and then I would just go through and solve the equation, which I know you guys can do. But when you're working with these mid-segments, a lot of times it might be helpful to think about it as 2 times the middle equals the 2 outsides added, and then you solve for whatever's missing. Now, as far as kites go, kites are a different type of quadrilateral entirely. So they don't fit in with parallelograms, they don't fit in with trapezoids. And so with kites, we have a quadrilateral. Now there's 2 pairs of consecutive sides that are congruent. So consecutive sides are sides that are next to each other. So as we look at the picture here, we see that this side and this side are next to each other, and they're marked congruent. And then on the other side of the picture, we have this side and this side marked congruent, and they are consecutive right next to each other. And so when we're looking at these kites, that's what we're kind of looking for, and it kind of looks like a basic kite if you've ever seen a kite before. And so that's why we call them what we are calling them. Now, the other thing then is opposite sides cannot be congruent. So when I'm looking at this picture, these 2 sides cannot be congruent, or else we no longer have a kite. If that were the case, if I had 2 consecutives and opposite sides congruent, that would actually be a rhombus, and we've already talked about those previously. So the 2 sides next to each other are going to be congruent, but the actual opposite sides will not be. Okay? Now, the other thing that's special about kites is that if I draw the diagonals in, so if I take a kite and I draw in the diagonal, what's going to end up happening is those diagonals are going to be perpendicular to one another. And so as I look at the picture here, once I draw my 2 diagonals in, they're always going to be perpendicular, which means if they're drawn in, all 4 of these middle angles are all going to be 90 degrees, just like a rhombus had. The other thing I want to point out here is that when I draw in my diagonals, and I'm going to highlight different ones here for a second, but when I highlight this angle right here, if I were to split it this direction, this top angle here, or triangle, is going to be exactly the same as this bottom triangle here. And so I can see that because I already have this side and this side marked, this side and this side marked, and then I have this shared side in the middle, and I have this two triangles that are completely congruent, meaning all the angles are congruent. So this angle would be congruent to this angle would be congruent to this angle, and then this entire angle up top here would be congruent to the entire angle down below. So if I draw that long diagonal in, I'm going to cut the figure into 2 congruent triangles, meaning all the different pieces. And so what's really important there is the idea that these angles on top and bottom, so here and here, would end up being congruent. Now on the other side of that, if I were to draw in the other diagonal, so now I'm going to highlight this one here. And so as I highlight this one, the 2 triangles on either side are no longer congruent. But if I notice on this particular triangle, I have this side and this side marked congruent. And if I remember my isosceles triangles, that means this angle and this angle will be congruent. And then on the other side, I've got this triangle that has 2 sides marked congruent. And if that's isosceles, that means these base angles are congruent as well. So not only do the perpendiculars give us 90-degree angles in the middle, but they give us a lot of other relationships that we can utilize to find other missing angles. And for kites, that's kind of the main idea that we're going to be working with, is how do we find missing angles within. So if we look at a couple examples here, in this first example over here, it says find the measures of the numbered angles in each kite. Well, so right away, if I have both diagonals drawn in, I know that the middle is all 90. So that means the measure of angle 1 is going to be 90 degrees. From there, I'm looking for angle 2. Now, if I look at this picture closely, I can notice that I have this right triangle right here, where I know the 90 and I know the 67. All I'm missing is this angle 2. And as we've done numerous times throughout the course of the year, I know that I can go ahead and take the 180 minus the 90 minus the 67, and what that leaves us with then is that angle 2 would have to have a measure of 23 degrees. And so in this case, we're using some properties of the kite, but also using properties of triangles and things that we've discovered in past sections. Now, if I look at the second example here, so on this side, again, as I'm working through this problem, the first thing I should do, if both diagonals are drawn in, all these middle angles are going to be 90 degrees. So that starts us off right away with angle 2 equal to 90. Now from there, a couple of different things to think about. We said that if we split up our kite this direction, where this side is congruent to this side, we knew that the base angles would have to be identical, which means if this bottom angle is 63, then angle 4 up at the top would also have to be 63 degrees. Not only that, but when we come to this other side on the other triangle then, so if I look at this second triangle over here, I know that if the top angle is 43 because of these two congruent sides, then this bottom angle must also be 43. Now the reason those two are important is because now if I want to find angle 3, if I split up my kite into this triangle right here, I've got this right triangle where I know the 90 and I know the 63, I can subtract those from 180 and the measure of angle 3 would come out to be 27 degrees. On the other side, I can do the same type of deal where I split my kite into this right triangle where I know the 90 and the 43, and if I go ahead and subtract those from 180, then I end up with a measure of angle 1 of 47. So as you're working through these kites, the middle angles are always going to be 90, and then from there, you're just using those isosceles triangles, or triangles add up to 180, and you're just kind of working your way around the picture. The last thing that I want to do is just kind of remind you of all the different relationships between our quadrilaterals. So quadrilaterals are the overarching theme of the chapter. We're all working with four-sided objects. Within that, though, there's three different families. So there's the parallelograms, there's the trapezoids, there's the kites. So three completely different families of figures. In the parallelograms, if we think about what's happening here, a parallelogram has a specific set of properties that it passes down to each of its different shapes below. So everything a parallelogram has, everything below is also going to have. And then we go to rectangle and rhombus, which have more specific properties. So they go even further than a parallelogram, and those two can also pass down properties to the last one, which is the square. And the square has anything that's up above it. So all of these sides are what we would consider a family of figures. They're all going to share properties within themselves. In our second family, we have trapezoids, which really only had the one kind of main property, and that was that one pair of sides are parallel. When we went to isosceles, we got that the legs were congruent, diagonals were congruent, and base angles were congruent, so they added quite a bit. And so that's another family of quadrilaterals that we can work with and use their properties to find missing pieces. And then kites are kind of their own standalone thing. And so kites were just the fact that two consecutive sets of sides are congruent, opposite sides are not, and then that the diagonals were perpendicular to one another, And so then we were able to find any missing angles within. So with that, you should be able to work through the worksheet that you get in class today or that you get off of Google Classroom. As you work through, as always, if you have any questions, make sure you ask in class or email or check the answer key as it becomes available, and make sure you have that ready to go when we turn that in a couple days.